Okay, Taylor and Joseph and Hunter and whoever else might have been absent or had gotten cut off or been absent because our internet crashed during 7th period. You'll see this in both OneNote and in Canvas. This is not an assignment, not something that you need to submit. But what we did today was we put some ideas together that we've been working on for a while now to find the area of a regular polygon. Remember that a regular polygon is a polygon that's both equilateral and equiangular. And it's important to know that this process can only be used on regular polygons. We have to come up with a different method if it's not a regular polygon. And so for each one of these regular polygons, we're looking for its area. And the process is we're going to find the area of a single triangle that starts at the center of the polygon. And once we find the area of that one triangle, we're going to multiply by 5 in the case of the pentagon, because there would be five such triangles inside the pentagon to give us the area of the pentagon. So our starting point is to find the measure of an angle. We're going to do some trig with this. So remember that if we do n minus 2 times 180, it gives us the sum of the interior angles for any convex polygon. This one's a 5-sided polygon, so when I do 5 minus 2, which is 3, times 180, it gives me 540 degrees. Well, 540 degrees is all 5 of these angles added up. So I'm going to, since it's regular, I get to split that 545 ways, and it tells me that each one of the angles of the regular pentagon is 108 degrees. But I need an angle in the triangle. So that 108 degrees gets split in half by the triangle that's here. And so I get two 54-degree angles. And it's that 54-degree angle that's going to allow me to do trig on this triangle to find its height. So again, I'm looking for the area of the isosceles triangle, but I'm going to use the right triangle that's half of that isosceles triangle to get the area, to get the height. So I'm going to isolate that half of that isosceles triangle, 54-degree reference angle, don't know the height. This length is half of the 16, which is 8. And SOHCAHTOA tells me that because I'm looking for the length of the opposite, knowing the length of the adjacent, I'm going to set up a tangent ratio. So tangent of 54 is equal to opposite over adjacent. I would end up having to multiply both sides by 8 here. And be careful not to use the wrong column in the trig table, which I did earlier. When I do 8 times the tangent of 54 degrees, it's going to give me 11. You'll go look that up in the trig table. I'm sorry. Oh. All right. Sorry, guys. So the tangent of 54 degrees being 1.37, so on and so forth. When I multiply that by 8, I end up with h is approximately equal to 11.011 centimeters. That's this height right here, 11.011 centimeters. Now I can find the area of this triangle. I have the base, I have the height, I can get the area by doing 1/2 base times height. So for the area of the isosceles triangle, 1/2 times base times height gives me an area of 88.088, I believe. Hang on. I get 88.088 square centimeters for the area of that one triangle. But since there would be 5 such triangles inside the pentagon, I now take that area and I multiply it by 5. And it tells me that the area of the pentagon is going to be 440.442 square centimeters. So you possibly see now that the ideas that we've put together is some of the interior angles of a polygon, split it because it's regular, figure out an angle on the triangle that allows me to figure out any missing lengths that I might need that would allow me to find the area of the triangle, find the area of the triangle, and then multiply by however many of those triangles there are. So that's the process we're going to use. The only other example I did in class was this example right here, and these are examples. You do have some different problems in Canvas that you need to do, but this one says find the area of a regular, equilateral, equiangular, 36gon, that means it has 36 sides, with a perimeter of 792 feet. I'm not even going to attempt to draw a 36gon, but I am going to draw one of the 36 central triangles just to visualize what's happening here. So if I can find the area of one triangle, I multiply by 36, it will give me the area of the 36gon. Need a couple pieces of information. One, I need a side length. Well, since it's regular means equiangular but also equilateral, each side is the same length. So if I split it 792 36 ways, it gives me 22 feet. So each side is 22 feet long. Each of the 36 sides is 22 feet long. Now when I put it on the triangle, that means I have the base of the triangle. I still need to find the height. In order to do that, I'm going to have to figure out this angle right here, or the other one, it doesn't matter. But remember that n minus 2 times 180, and since it's a 36gon, 36 minus 2 is 34, and 34 times 180 is going to be 6,120 degrees. That's the sum of the interior angles. But I know that since it's regular, I can split that sum 36 ways, and when I do that, I get 170 degrees for each interior angle. Now, there is no 170 degree angle on this triangle. Remember that if I continued to draw this 36gon, which I'm not even going to attempt to do, that each angle of the actual 36gon is 170 degrees. But when I draw one of those triangles, it cuts that 170 degree angle in half. Half of 170 is 85. So now I know an angle in the triangle as well. So I'm going to be able to use trig to find that height. So just redrawing it. Actually, let me just redraw the right triangle for which I'm going to apply SOHCAHTOA, or right triangle trigonometry. 11 feet, because the height cuts that 22 and a half. 85 degree angle, unknown height. We're looking at a tangent ratio again. Need the length of the opposite, knowing the length of the adjacent. So tangent of 85 degrees is equal to h over 11. By multiplying both sides by 11, it will allow me to solve for the height. And the tangent of 85 is actually 11 point something. 11.43, so 11 times 11.4300523. That is the height, and this is going to be a surprisingly big number. So when I multiply that height by 11, I get a height of 125 feet, 125.731 feet. And that might seem, when you first look at it, that might seem like that can't be right. That's way too big. That in this triangle where I have this length is 11, why would this length be 125? But let's think about it from the perspective of the angles. Across from that 11-foot side is a 5-degree angle. That's a teeny tiny angle compared to 85 degrees and 90 degrees. So it's safe to assume that the other two side lengths, the one across from the 85-degree angle and the hypotenuse across from the 90-degree angle, are going to be much, much longer than that 11-foot side that's across from a 5-degree angle. So there's nothing wrong with this height. It is fine. And now I can work on finding the area of one of the 36 triangles in the 36gon. So I'm going to say the area of one triangle is 1/2 base times height. Some people prefer to do base times height divided by 2. It really doesn't matter. It's the exact same thing. And when I do that, I get the area of one triangle is approximately 1,383.036 square feet. Because a 36gon will have 36 of these triangles, I'm going to multiply that by 36 to get the area of the 36gon. And it's a big number, but that's okay. This is a big polygon. And the area of the 36gon is 49,789.308 square feet. Anyway, that's what you missed today. There are 4 problems in Canvas for you to do for homework. It looks like 6 when you open it up, but 2 of them are the pictures that I'm going to take a look at. So take a picture of your work, submit it. Also, there is a warm-up in Canvas that's just 2 trig problems, so get those done as well. Anyway, hope to see you tomorrow. Bye.